Today, what the entire lab is doing is trying to design chips specifically for cryptographic computing, or sometimes it's called privacy-preserving computation. And the idea here is to leverage emerging forms of cryptography to compute directly on encrypted data and give users unprecedented levels of privacy and security. So this sounds great, and it is. It has enormous potential. The problem is that it's typically 1,000, 10,000, even 100,000 times slower than the codes that we're using today. So what we're trying to do is build all the infrastructure that we need to bridge that performance and usability gap to make it practical. Welcome to my office. I'm Brandon Reagen. I'm an assistant professor here at NYU Tandon in the ECE department, and I'm specifically a computer engineer. I'm a computer architect, so what we try to do is actually design chips. So we figure out how to design them to get the most performance out of them as possible. And traditionally how this was done is we would build really general chips. And so general chips are really good at basically processing anything. And what we're trying to do today is build more custom chips. So rather than being able to process everything well, we're trying to do one thing or one specific application extremely well. And the potential here is that these specialized chips, sometimes we call them accelerators or custom hardware, they can typically achieve 2 to 3 orders of magnitude more performance than the general ones. So historically, I've applied that to machine learning, tried to make machine learning go really fast. And since joining NYU about 5 years ago, I've been focused on cryptographic computing, which is trying to do things like computation directly on encrypted data. There's 2 major challenges that we have to solve. The first one is usability. So it turns out trying to just use these technologies is really hard. So you can't just take your plain text program and plug it into these cryptographic computing schemes. There's actually a major translation challenge there. So what we're doing is actually developing the frameworks and specifically compilers that will automatically translate the codes that people are running today into cryptographic computing. Now, once we have those, that's where we get this 10,000x speed up, and that's where we have to go in and design custom chips. So there's a bunch of different things that we're trying to do. We're doing everything from building custom multipliers, custom data paths, custom architectures, custom memory systems, just everything from basically gates to entire computing systems is being customized and tailored to the needs of cryptographic computing to make it go much better. And today we have 3 to 4 unique accelerator designs that can address these problems. We have the opportunity to break what I like to think of as the privacy utility trade-off, right? So today, if I'm a user of a service, it's typically running in the cloud, and if I want to get high quality results out of that service, I have to provide my sensitive data. I have to give that to the cloud. I have to trust them that they're going to use it correctly, and that's fine. I'll get really good answers out of it, but maybe I don't want to rely on trust, right? Because right now I can either get access to a high quality service and give up my personal sensitive data, or keep my data and not get access to that service and sort of miss out. With these cryptographic computing technologies, you get the best of both worlds. Your data, every bit that leaves your, say, smartphone, will be fully encrypted. It'll be sent over to the cloud encrypted, it'll be processed encrypted, and even the result is encrypted and it comes back to you, and you'll get the exact same result that you got in the technology how we do it today. So if we can achieve this 1,000 to 100,000x speed up and automatically map programs to this technology, there's great potential, I think, for the general public, and that's why we're all so excited to work on this. So in terms of trying to map the workloads of today into cryptographic computing, and specifically let's talk about fully homomorphic encryption, which is an emerging encryption technology that allows you to do computation directly on encrypted data. So doing this mapping is not trivial, and the challenge is that there's a lot of constraints when we use this technology. So for example, the operators, the only data structure that you have in here is a very large one-dimensional vector. And when I say very large, I mean like 2 to the power 16, so it's massive. And then on these vectors, you can only do 3 operations. You can do element-wise addition, element-wise multiplication, and you can rotate the vector. So with those two things, it's very hard to express your computations. And then there's another layer of complexity, which is that you can only do a certain number of computations before the whole thing just falls apart. So you have to be very careful about how you structure your computations, and you have to insert these operations called bootstrapping, which will allow you to do more computations before things fall apart. So to address these problems, we've recently released an open source framework called Orion. This was published at ASP+ earlier this year. It got the Best Paper Award. It's being widely used amongst the community. And what Orion does is it will take your machine learning program that's written in PyTorch and automatically map it into fully homomorphic encryption, taking into account and addressing all of these constraints, and it will get the right result, and it'll do that all automatically. So you don't have to worry about anything. As long as you can write PyTorch, you can use fully homomorphic encryption. So we're quite excited about that result, and what we found is that not only can we do that automatically, we can also run much larger workloads than anyone previously could. So we also are able to execute the largest fully homomorphic computation that's publicly known to date. And we do all of that while achieving more performance than all the other compiler frameworks. So we also have state-of-the-art performance, which is great. We've since extended that pretty significantly. So now we can also do neural recommendation, which is what a lot of data centers are running, companies are running to service ads and things like that. So we can run those under fully homomorphic encryption. And we just recently announced a general matrix description language. So any matrix computation or tensor computation that you also want to do, so you can also use that in FHE. So how I got into this field was two things. The first was, as someone who likes to design chips to get extreme performance, this was kind of like a major challenge that I saw. The other thing that got me really excited is that this is a new way of thinking about data sharing, and it could potentially open up like truly groundbreaking applications if we can make it work. So for example, we could go back to, let's say, fully homomorphic encryption. So right now, I would never share my medical data, right? It's just not something I would ever consider doing. It's extremely personal. But if there was a global, say, database of everyone's medical record, a lot of scientists and doctors could probably observe patterns that could make breakthrough revelations about treatment. If we could actually make this cryptographic computing stuff in fully homomorphic encryption practical, maybe there's a way where I could put medical records fully encrypted, never could be tied back to me, never decryptable by anyone, and doctors could run computations on this database to make these discoveries without sacrificing the privacy of everyone. And that gets me excited about doing computations that we can't do today and where this technology could take us and allow us to advance.